This is the video lesson for section 4-3 on vectors for John Allison's trigonometry class at Pulaski Technical College. The first question we need to ask ourselves is, what is a vector? And a vector is a directed line segment. Or a line with direction and distance. A vector is usually drawn with an arrow or a ray. The tail of the vector, or the origin of the vector, is known as its tail or its initial point. The head of the vector, or the arrow end of the vector, is known as its terminal point. The magnitude is the length of the vector, or the distance from the tail to the head. It's important to know that the length of a vector is simply a number. It's just a measurement of how long the vector is. Two vectors are called equivalent if they have the same magnitude and direction. The black vector and the green vector have the same distance and they're oriented in the same direction, so those are equivalent vectors. Vectors with the same magnitude and direction. A scalar is just a new word or another name for a constant or just a number. A scalar is not a vector. A scalar is just a number. We say two vectors are scalar multiples of each other. If they have the same direction or the opposite direction, but different magnitudes. For instance, if this vector and this set vector are oriented in the same direction, or this vector oriented in the exact opposite direction, these are scalar multiples of each other because they have the same or opposite directions but different magnitudes. Let's talk about our notation for vectors. Vectors are usually named with letters. For example, this vector might be called vector A. When I'm writing the name of a vector, I will usually include the letter with an arrow over the top of it. This notation indicates the vector A. It can be a capital letter, it can be a small letter, it could be a combination of letters. For example, this vector could be called XY. Another notation for vectors your book will often use, instead of putting an arrow over the top, your book may call a vector with a letter in bold print. So the vector A in bold print is a way to denote the vector A. Usually when I write, I don't do this because bold print's hard to constantly do when you're writing. Notation for the magnitude of a vector. Is sort of like a double absolute value around the letter or the name. This is the magnitude of the vector A. Another important thing to know about the magnitude of a vector is the magnitude is always positive. This, in bold print, might be the way your book will represent the magnitude of a vector A. This should have been use the same notation as what was for the name of the vector. We don't want to mix capital and small letters when we're naming vectors. Now that we know what a vector is, we need a better way to describe it so that we can identify its direction and its magnitude. To do this, we're going to introduce the vector considered on a coordinate plane. If we let V be this vector, we can consider the distance as the shortest distance traveled between the initial point and the terminal point on the vector. But we can also consider this vector by considering its horizontal component and its vertical component. We're going to call the horizontal component A and the vertical component B. And that's simply if we left the initial point and traveled to the terminal point, only traveling horizontally and vertically. The horizontal component is the distance that we travel with direction. To the right would be a positive value for A. If we travel to the left, it would be a negative value for A. Same with the vertical component. If we travel up, it's a positive value for B, and to travel down is a negative value for B. In this case, we're going to introduce a new notation and say the vector V can also be denoted as, for vectors, we're going to use this bracket that looks kind of like a less than sign, the horizontal component, then the vertical component, and close the bracket that looks like a greater than sign. If we count the units for A, we go from -2 to -1 to 0 to 1. The horizontal component of this vector is 3. The vertical component, we go from 0 to 1 to 2. The vertical component is 2. So this notation allows us to indicate the direction of the vector. If we were to consider this vector, we'll call this vector W. If we leave its initial point and go to its terminal point, horizontally and vertically, the horizontal component would be 1, 2 units. The vertical component would be down this time, 1, 2. So the vertical component would be -2. So the vector W, using this notation, would be represented by 2 for the horizontal component, -2 for the vertical component. Recall that it doesn't matter where the vector is in the plane. This is a different vector, but it's an equivalent vector. We'll call this vector U because its horizontal component is still 2 units right. Its vertical component is still 2 units down. So if we were going to describe the vector U using this notation, it would be an equivalent vector with the same horizontal and vertical components. Also notice that this notation in identifying the horizontal and vertical components of a vector gives us a really easy way to find the magnitude of a vector. In this case, if we look at the vector U, the magnitude of U is the length of the vector. Its horizontal component forms one leg of a right triangle. Its vertical component forms another leg of a right triangle. So we have, in this case, if the horizontal component's A and the vertical component's B, that the magnitude squared is equal to the horizontal component squared plus the vertical component squared using the Pythagorean theorem for right triangles. If we take the square root of both sides of this equation, we'll get the magnitude of the vector U is equal to the square root of the horizontal component squared plus the vertical component squared. So if we wanted to find the magnitude of W, we have its horizontal component and its vertical component, we simply do the square root of 2 squared plus -2 squared, which is the square root of 4 plus 4, or the square root of 8. And the magnitude of W is the square root of 8. course, you can simplify that and write that as 2 square roots of 2, but I'm okay with the square root of 8. Of a vector u. Another thing we need to know is what's called the direction angle of a vector u. The direction angle can be found by making an equivalent angle with its initial point at the origin, or simply moving the vector so that its initial point is at the origin, finding its magnitude using the horizontal and vertical components. Here, for this vector u, horizontal component is 2, the vertical component is 3. The direction angle theta can be found if, when placed with its initial point at the origin, if the vector lies in the first or second quadrant, then the direction angle theta is equal to the cosine inverse of A, the horizontal component, over the magnitude of the vector. So in this case, our A is 2, and the magnitude of the vector u is the square root of the horizontal component squared plus the vertical component squared, square root of 4 plus 9, or the square root of 13. So that theta is equal to the cosine inverse of 2 over the square root of 13. Your book is using degrees, so we'll go ahead and use degrees. So when I do cosine inverse of 2 divided by the square root of 13, this tells me that theta is equal to 56.31 degrees. That's the direction angle. The angle between the vector and the positive x-axis when the initial point of the vector is placed at the origin. That is how you find theta if the vector is in the first or second quadrant when the initial point is placed at the origin. If the vector lies in the third or fourth quadrant when its initial point is placed at the origin, then theta is equal to the opposite of cosine inverse A over the magnitude of the vector u. So let's look at a vector let's call this vector v. We'll start with the initial point at the origin. Here, the horizontal component is negative 1.5. That's our A. The vertical component is negative 3. V is given by negative 1.5, negative 3 in those funny brackets. Our A, our horizontal component here, is negative 1.5. The magnitude of V is the square root of negative 1.5 squared plus negative 3 squared, which is the square root of 2.25 plus 9, or the square root of 11.25. So that our angle theta, because this vector lies in the third quadrant, is given by the opposite of cosine inverse, negative 1.5 horizontal component over the magnitude of our vector, which is the square root of 11.25, or our calculator tells us this is negative 116.565 degrees. Now that we have this new way to represent vectors, let's say we have two vectors, u, and let's say that u is the vector 3, negative 2, and v is the vector negative 4, 3. This allows us to do some fundamental vector operations. You've already learned to find the magnitude of u and v. The magnitude of the vector u is the square root of its horizontal component squared plus its vertical component squared, or the square root of 9 plus 4, square root of 13. The magnitude of the vector v is the square root of its horizontal component squared plus its vertical component squared, or the square root of 16 plus 9, the square root of 25, or 5. But we can also find the sum of two vectors now. This is the vector 3, negative 2, plus the vector negative 4, 3. When we add two vectors, we get what's called a resultant vector by adding the horizontal components to get the new horizontal component and adding the vertical components to get the new vertical component. The resultant vector, u plus v, is going to be negative 1, 1. We can also multiply a vector by a scalar, and recall a scalar is just a constant. For instance, 3 times the vector u is the same as 3 times 3, negative 2. To multiply a vector by a scalar, we simply multiply the horizontal and vertical components by that scalar. So 3 times the vector u becomes the vector 9, negative 6. To multiply the vector v by negative 2, this works the exact same way. 2 times the vector negative 4, 3. We multiply negative 2 times the horizontal and the vertical components, and we get the vector 8, negative 6. You can combine these operations and find 4v minus 5u. That's the same thing as 4 times the vector v plus negative 5 times the vector u. which is 4 times the vector v is negative 4, 3 plus negative 5 times the vector u is 3, negative 2. So this would be the vector negative 16, 12 plus negative 15, 10, or negative 31, 22. Another vector operation is called the dot product. This is not multiplication like you're accustomed to. The dot product, u dot v, is given by the product of the horizontal components plus the product of the vertical components of the two vectors. Negative 12 plus negative 6 is going to be u dot v is negative 18. And notice the dot product is a scalar. It's not a vector. It's a constant, not a vector. For any two vectors, where u is a, b, and v is c, d, where a and c are the horizontal components of the respective vectors, and b and d are the vertical components of the respective vectors, u dot v is equal to v dot u is equal to the product of the horizontal components plus the product of the vertical components, and always a scalar. If two vectors are perpendicular to each other, when their tails are placed together, then u dot v will equal 0. Let's look at an example. It's easy to see. Let's look at the vector with horizontal component 3 and vertical component 0, and the vector, we'll call this vector u. Let's let the vector v be the vector with horizontal component 0 and horizontal or vertical component 4. Then u dot v would be the product of the horizontal components, or 3 times 0, plus the product of the vertical components, or 0 times 4, which would equal 0 plus 0, or 0. It's very obvious that these two vectors, when their tails are placed together, would be perpendicular and form a right angle. Anytime the two vectors are perpendicular, their dot product is 0. One more thing we're going to talk about vectors in this lesson: unit vectors. We say The vector v is a unit vector if its magnitude is 1. In other words, if the magnitude of v equals 1. There are two extremely special unit vectors. One we call I, sometimes referred to as I hat, but in your book it's a bold printed I. This is the vector 1, 0. Horizontal component is 1, vertical component is 0. So it's obviously a magnitude 1. The other is the vertical unit vector, sometimes called j hat, or in your book, a very bold j. This is the unit vector with horizontal component 0 and vertical component 1. And again, very obviously, a unit vector whose magnitude is 1. What this allows us to do is to write any vector as a sum of a scalar multiples of these two vectors. For instance, if we let v be the vector 2, -3, we can say that that's the sum of the vectors 2 times 1, 0 plus -3 times 0, 1. 1, 0 is I, or I hat. 0, 1 is bold j, or j hat. So this vector v can be represented as 2i hat minus 3j hat, or 2i minus 3j, where I and j are the unit vectors, the horizontal and vertical unit vectors, respectively. It's important to know that you can find a unit vector in any direction by simply dividing the vector by its magnitude, or multiplying by the reciprocal of its magnitude. Let's look at this vector v. If we want to find a unit vector in the direction of v, first we find the magnitude of v. Remember, that's the square root of the square of the horizontal component plus the square of the vertical component. Square root of 4 plus 9 is the square root of 13. Next, we multiply v by the reciprocal of the magnitude of v. The unit vector in the direction of v is given by 1 over the magnitude of v times v, which in this case is 1 over the square root of 13 times the vector 2, -3. Like before, we distribute the 1 over square root of 13, and we see that this unit vector is 2 over the square root of 13, -3 over the square root of 13. This is the unit vector in the direction of v. it's important to know that we can perform operations on vectors written in terms of I and j. Let's let u equal 3i hat plus 5j hat, and let's let v equal negative 2i hat plus 4j hat. Then the resultant vector u plus v is simply the sum of the horizontal components, and the horizontal components here are 3 and negative 2 respectively. So 3 plus negative 2 times I hat plus the sum of the vertical components 5 and 4 times j hat, or 1i hat, or just I, plus 9j hat, or I plus 9j. The dot product of u and v, u dot v, is still the product of the horizontal components 3 times negative 2 plus the product of the vertical components 5 times 4, in this case negative 6 plus 20, or 14.